Welcome to the lectures on evolution of air interface towards 5G. So, till now we have had overview of the different waveforms that are there in the second generation and third generation. And today, as you can clearly see that we are going to discuss the topic, which is sorry, this is a wrong title that we have. It is for the fourth generation system, and we will be talking about the waveform in 4G, and primarily it will be about OFDM. Now, a brief few words before we get into the details of the discussion. OFDM, as today we will discuss, is a primary waveform. We have laid the foundation when we discussed the multi-carrier FSK. So, when we discussed the multi-carrier or emery FSK, we had pointed out that the system model would remain the same, which served as the basis for discussion of 2G, and the same waveform or the same structure will be useful when we discuss the fourth generation and beyond systems. So, we had also discussed how the emery FSK could be designed in a manner that the frequencies that are being chosen for operation are orthogonal in nature, and we had also said that since they are orthogonal, it is possible that you not only use them for switching between the carriers and letting information flow by virtue of choice of a carrier, you can actually use all the carriers simultaneously, and that would appear as FDM. And since these carriers are to be chosen in an orthogonal manner, it can serve as a basis for orthogonal frequency division multiplexing, and today we take this opportunity to get into the details of it. Now, other reasons why this is critical and important, because this is a foundation on which most of the modern generation communication techniques are built. So, it is kind of a platform, one can say. It is a multi-carrier technique, and although we are discussing 4G, but when we get into the fifth generation, we will see that fifth generation essentially stands on the same structure as in 4G, although there are certain variations in the frame format and the way things are used compared to the fourth generation, but the fundamental element is still fourth generation or the OFDM system. And we will again see today that it is not only the baseline for 4G and 5G, it is also the baseline for broadband wireless local area network. It is also the foundation for broadband metropolitan area networks. It is also a standard for digital audio broadcasting, for digital video broadcasting, as well as for the satellite high speed satellite communications. So, it is a very, very important waveform as on date. So, we do not know what is going to happen after 10 years from now, but it is very important to study it and build our basics, so that we can understand most of the communication systems which are usually available for commercial purposes. It has several advantages and there are certain disadvantages. So, our aim would be to understand as much details as possible, and that would also give us a key and insight into developing newer waveforms based on whatever we have discussed earlier, as well as whatever we are going to discuss in this particular lecture. So, moving ahead, when we talk about 4G, it is essentially IMT advanced. We have already said that, and this uses OFDM as it is written over here. So, when we talk about 4G, the main word that comes to our mind is the OFDM technology in terms of air interface. So, it is a very important method, as we have already said, because it is used for wireline communication. It is used for wireless communication, namely satellite. We will see that. It is used for local area networks. We have already said that. It is used for 4G as well as its extended version in 5G. So, not only that, it is one of the primary multi-carrier techniques. So, it is a multi-carrier because we will see how this multi-carrier concepts come in. We have already discussed it once. So, the general class of multi-carrier techniques have a basis, or it can be studied in the perspective of OFDM. There are other views also where OFDM can be seen as a subset of the overall class of multi-carrier, but this being very, very popular, it is also good enough to study OFDM, and because it is easier compared to other methods, and one can digress and move into other techniques and understand them. So, a brief into the history about OFDM. What we can see that it was initially used in the military systems, and that was around the 1960s. In this period it was used in different military systems, and these are the different names of the technologies that were using them. So, it is not a new method, that is a primary thing. Although it is very popular these days, it is being used in every wireless broadband communication system, but it has been existed for almost 60 years now. And traditionally when it started to happen, what we see is that there was a bank of conventional transmitters and receivers. So, this is pretty normal, because we had discussed emery FSK as the foundation, as we just said, and these separations were delta f, and we had found the relationship for these. So, we said that you are going to use all of them simultaneously, and in each of them we said they had a model like e to the power of j 2 pi f k t. This is the carrier where this f k equals to 1, 2 and so on up to n, or you could also index k as minus n by 2 up to n by 2 minus 1. So, then there again you will be having n carriers, and each of these carriers would be getting an x k, which is a signal from the constellation and will be sent out. So, what we will get from the first one is x 1 e to the power of j 2 pi f k t. The second one is going to produce x 2. So, this is f 1. Second one is going to produce x 2 e to the power of j 2 pi f 2 t, and so on, and the last one is going to take x n e to the power of j 2 pi f n of t, and each of these x 1, x 2 up to x n, these are element of some constellation of order m. What it means is that each will be drawn from a constellation. Let us say we are drawing the constellation diagram for 16 QAM. So, each symbol will be drawn from them depending upon the bit sequence. Now, it can also be noted that each of these symbols that are coming in, they need not necessarily be drawn from the same constellation. It could also happen that some of these carriers take from, let us say 16 QAM, while the rest of them can take from 64 QAM or any other combination, it can happen. So, this is a generic model, it is a generic system layout, it is a generic equation, generic framework, and we have said that the same foundation or the same expressions that were used will be useful in studying all the future things. So, here what we see is that each one of them has a multiplication operation over here, right. So, each one has a multiplication operation, each one has a multiplication operation. So, that means there would be an oscillator in each of the lines. So, that means there is a signal constellation x k, which is multiplied by a local oscillator which has a frequency of f sub k, and then it goes out, right. That is for each of them, and finally, they go out together. So, in the air medium you have a summation of x k e to the power of j 2 pi f k t sum over all k, and this is your time domain signal that goes into the air. So, this is what we are going to see. So, at each point there will be a multiplication of the oscillators. At the receiver, what we see is that we have again discussed the orthogonality criteria, where we said that at the receiver side whatever signal is received. So, if let us say this whole signal is received and we demodulate it by multiplying e to the power of minus j 2 pi f k prime t, and we are going to integrate, because it is continuous time, from 0 to capital T, which is the symbol duration dt. You can do it in a summation format also. So, what you will find is that when this frequency index is not equal to this frequency index. So, that means when k is not equal to k prime, then this entire thing would end up in 0, and when k is equal to k prime, you will find that the entire thing will end up in x sub k. That means, the product would be 1, the sum of the entire multiply, accumulate and integrate operation would be 1, otherwise it is 0 by virtue of orthogonality. A digression from this particular discussion, but which is absolutely in context, what you can also visualize is when we talked about the spread spectrum system. Essentially what we are saying is that this particular signal, that is what we are multiplying, is kind of acting as a spreading signal. One can think of it in that manner also. So, here what we have is that the weights are drawn from exponential function, whereas what we discussed there is a more general one, where the codes could be drawn from any function. Hadamard is one particular way of generating orthogonal codes. Here if we connect to this, we can think of DFT matrix, which we will see could act also as generation of codes. So, this one can see it as a generalized picture through which one can study either spread spectrum or even multi-carrier systems, where it is kind of n dimensional signaling as such, and we have discussed the n dimensional signaling in the past. So, if one is comfortable with the notations or description as basis functions, so what we have these as let us say we can write them as S m, rather we will not write this S m, or let us say f prime of k, this entire thing of t. So, this is a basis function. So, we have n basis functions, the codes, if they are orthogonal, they are again n basis functions, and at the receiver one can think of either a matched filter operation. I mean, here what you see is the correlation. So, when you implement the matched filter as an impulse response, you convolve. So, essentially it turns out to be an correlator receiver, because finally you will be sampling at this time instant t. So, one can also visualize this in terms of n dimensional signal with n basis functions and a matched filter operation at the receiver with the particular basis function. So, we project the incoming signal on the different basis functions, read the outputs and then process it further. So, if you see it in this way, then it is a generic representation, you can study all the schemes in one particular platform. So, now going back again to the way it was developed, in 1971 it was shown that DFT could be used instead of the bank of conventional transmitters and receivers. So, this entire set of n number of oscillators. So, we would have had n oscillators at the transmitter and n oscillators at the receiver. So, we have at the transmitter and at the receiver both sides. So, those could be reduced and one can use a DFT operation. Now, DFT operation, the advantage is it can be implemented in digital circuit. It will be much low powered compared to this entire set of oscillators that are to be used. So, this was a turning point when it was not restricted to defense applications, because cost is an important factor. So, things could become easier to implement, and with the advent of FFT, which could realize a DFT operation even at lower complexity. So, order of n log n is the complexity. So, one could finally realize OFDM in a more easier fashion, and OFDM techniques were getting used, especially in devices where power was a critical factor. So, today when we look at things, we have handheld devices, and most of them are power critical, because we would like the battery to last longer. So, if we would have had this kind of methods which use oscillators, we would have been able to get only a limited gain, but because we could implement in digital circuits and we could use FFTs, the gains of OFDM became much more useful, much more translatable, and there was a proliferation of different techniques which could use OFDM. So, it started with this HDSL, as we are seeing HDSL, that is what is written here. So, that is high bit rate digital subscriber line, where it was used. Then there was ADSL, where OFDM was also used, very high speed digital subscriber line, and at that time it could produce 100 megabits per second, which was a very large data rate at that instant of time. And as said earlier, it was also introduced into the wireless domain through digital audio broadcasting, you can find the specifications in a particular reference which we will point out, and it was also proposed for use in WLAN, that is wireless local area network. In wireless local area networks, there were two proposals. This particular proposal was from European region, which is HyperLAN, and this is, as can be seen, it's an IEEE proposal. And what we have today, this is somehow more popular, and you usually associate the term Wi-Fi with such a technology, that is wireless fidelity, and there are different forums which address it, but primarily it is the 802.11a which got OFDM into the systems. In this series, there was 802.11b which did not use OFDM, but then there was 802.11g which again used OFDM, and it kind of superposed 11a and b in a manner that it could interoperate with the earlier standards, and it was also designed for the 2.4 gigahertz ISM bandwidth, ISM band. This was primarily for the 5 gigahertz band. So, in the this basically translated the 11a into the 2.4 gigahertz band. Then there was 802.11n standard, which is basically extension of OFDM with multiple antennas. And after N, it was 802.11ac, which started supporting MU-MIMO, multi-user MIMO. We will get an opportunity to see them, and finally, it is getting evolved into 802.11ax, which is supposed to get finalized sometime next year. So, all of these are still having OFDM as their primary baseline physical layer. So, there is a huge number of devices which are going to operate with OFDM, and there is a huge number of devices which is already operating with OFDM. So, it is very important that we look into it, understand it in such in details that we can take care of the problems which it is still facing. The wireless metropolitan area network also used OFDM. So, you can see that almost every broadband access system is using OFDM, and it is popularly known as WiMAX. This particular name is more popular, just like Wi-Fi was more popular instead of 802.11a. WiMAX is kind of more popular in this domain, and it is the 802.16 series of standards, primarily 802.11m, which was the contending technology for 4G and is also branded as the 4G technology. So, what we see is that there is a huge number of different standards which are using OFDM because of several advantages, right. So, we will get into the details and see how it is helpful. So, just a brief comparison of the application scenarios. What we see is that it is used, since it is used in WLAN, WMAN and WPAN. So, right from cell radius of a few kilometers up to few tens of meters of distance, it is useful, and it could support high and low mobility, right, and it could also operate in different frequency bands. So, these are so it has a huge dynamicity associated around with it, as a huge flexibility, and although it is so easily said and done, it is important that we get into the details of how it operates and what benefit it brings. So, since we are talking about the IMT advanced or 4th generation communication systems, and we have said that this particular air interface brings in a larger amount of spectral efficiency, a higher amount of spectral efficiency. Amongst the different things which brings in spectral efficiency, we had showed QAM, so quadrature amplitude modulation. What we see over here is the picture of a 64 QAM signal space diagram. So, that is also written over here. It is a signal space diagram for the 64 QAM, and you can count there are like 64 such dots, 8 across column wise and 8 across row wise. So, they are 64 in all, and each position in this particular constellation diagram indicates information carrying symbol. So, this particular signal for instance would be having the notation 3 plus j, because this is the j axis, the I axis, this is the j axis, and this particular signal constellation is going to be noted as 1 plus rather minus 5 j. right. So, like this you are going to have all these constellations marked, and depending upon the bit sequence that comes in 0 1 1 0 0 whatever it is, one has to take 6 bits, at least 6 bits at a time, because you have 64 which is equal to 2 to the power of 6. So, 6 bits are required to select one of these points, and the way these points can be arranged is like gray coding can be used, where the difference between the neighboring symbols is at most 1 bit. This is also very important, because this would reduce the error probability when there is a symbol going into error. So, if you are decoding, let us say, this particular constellation point, and instead of this one makes a mistake of decoding this constellation point, at most 1 bit would go into error if we are using gray coding methodology. So, this is something which you have studied in digital communications, which you know. So, it applies directly in such systems. Okay. So, now when we start discussing OFDM in details, as the name reads out, the most prominent part is to be remembered, it is a frequency division multiplexing. This is very, very important. So, what it means is that there are different carriers, and these carriers are multiplexed. So, since we are talking about carriers, it is a frequency carriers, they are frequency division multiplexing. So, when we look at a classical frequency division multiplexing system, we have one carrier here, let us say F1, we have another carrier here F2, and this is the spectrum occupancy or the spectrum characteristics of each of the carriers. So, to avoid signals from leaking one into another, one would specify a certain amount of guard band. The reason one has guard band, because let us say the signal dies out like this, right. So, when one is demodulating this particular desired signal, one can get a significant amount of adjacent channel interference. So, one can get adjacent channel interference. To avoid adjacent channel interference, if I increase this separation to a good amount, then the adjacent channel interference can be reduced, because under all circumstances it is never possible to have a ideal Nyquist filter, that means one which falls down vertically. This kind of a thing is not possible. So, one would always get a stretch in the frequency domain. So, one way to reduce the stretch, one way to reduce the overlap is to increase the separation through guard bands. So, if one does this, one can clearly see that this is something which one has to use only to improve the signal quality. And why are we looking at this? Because it is band, it is a band of frequencies, spectrum is very, very costly, we all know this thing very well. So, better ways to improve or improved ways to utilize the spectrum is very much important. And we have said that spectral efficiency is one of the terms. So, when you talk of spectral efficiency, what we effectively mean is that given a certain bandwidth, so this is a certain amount of bandwidth given in hertz. So, if I am using a spectrum like this, this is simply wastage, we can call this as a wastage, because you are not using it to send information, but rather you are using it to increase the signal quality, which you have to in order to maintain the QoS. So, when we look at OFDM, things are better. It is one reason for using OFDM, because it is the best possible modulation or multiplexing method which can give the highest possible spectral efficiency. So, if we look at OFDM, what we find is that this is again the frequency axis as the same as in the previous picture, and the spectrum overlap, what you see is that this spectrum there is an overlap, clear overlap. So, if this is my desired frequency of operation, what you see is that this portion there is an overlap of the adjacent channel frequency, and there is an overlap of the adjacent channel frequency on the left and right hand side both. Also the other components, that means if we take this particular carrier, this carrier is also going to produce interference. So, there will be lot of overlap. But now, although we are doing this, so compared to the previous picture, the advantage here is that if this is the desired peak, as has been pointed out, the subcarrier peaks, what we see is that the null occurs at this point. There is a null. Okay. So, null means all the different subcarriers, they have a zero crossing at this point. So, if they have a 0 crossing, when we are using this particular carrier to demodulate the signal, we are not going to get any impact of the adjacent channel interference. So, and why can this happen? Because we have already discussed the orthogonality criteria. We discussed in the previous class, and we also mentioned in today's beginning part that each of these carriers, which you are calling as subcarriers, they are e to the power of j 2 pi f k t, and the neighboring carrier is e to the power of j 2 pi f k prime t, right. So, if we try to see the projection of one on another and take the integration over the interval 0 to t, and this is exactly what we have done to check the orthogonal or to find the condition for orthogonality. So, the condition for orthogonality gave us that if f k minus f k prime should be equal to 1 upon t, this is the same symbol duration t that we are talking about, this is basically the subcarrier spacing, then one can get orthogonality. So, we have used this criteria to get our signal. So, since we have used this criteria to get our signal, this would obviously mean that they are overlapping with each other, because the subcarrier bandwidth is kind of spreading on both the sides, whereas we are placing the subcarrier at half that interval. So, although they are overlapping, by virtue of orthogonality, one is not getting any influence of any neighboring subcarriers. So, this way one can save a huge fraction of bandwidth, and this is the smallest spacing that one can think of. So, when we discussed MSK, we did say that the minimum term comes because of the smallest separation that is possible, and that is by virtue of orthogonality. So, this is a animated picture which helps us understand what is actually happening. So, this particular version is kind of a general FDM, you can say, okay. And if we let it change, then what we will find is that now these are orthogonal to each other. That means, the peak is coinciding with the nulls of all other subcarriers, and then what we result is in OFDM. So, basically in this blank, this orthogonality has come in to give us this particular result, and as you can clearly see that there is a huge saving in bandwidth by virtue of using orthogonal carriers, and although they are overlapping, they are not interfering with each other, and one can decode the signals. So, this is one of the main reasons why OFDM is so popular and is being used as a major technique in all possible broadband wireless communication systems, where spectrum is very costly, and one would like to make the best use of such a spectrum. So, we close this particular discussion over here, and we will take on further discussions in the future lectures. Thank you.